Now, suppose that someone gives us a rational number written as a fraction and we want to convert it to a decimal. Well, that's actually pretty easy to do. We just can long divide. So what we do is we have a numerator, we have a denominator, and what we do is we long divide the numerator by the denominator. And so we set up this kind of thing. Let's take a look at an example. Let's take 11 over 4 and write it as a decimal. So it's equivalent as a decimal expansion. So what do? I take 11 divided by 4. And what I understand here is that after this 11, there's a decimal point and just an infinite army of zeros, as many as I may need. And now let's see what happens. So I say, well, 4 goes into 11 2 times. By the way, I put the decimal point right above wherever it appears here. 4 times 2 is 8. When I subtract, I have 11 minus 8, which is 3. And now what I do is I bring down one of my 0 soldiers, and I take 4 and ask how many times does 4 go into 30? Well, that's actually 7 times, because 7 times 4 is 28. So when I subtract, I get 2. I bring down another soldier, and I see 4 goes into 20 exactly 5 times. 5 times 4 is 20, and I see now a remainder of 0. When I hit 0, I know I can stop. So I stop, and I see that, well, 11 over 4 is equal to the decimal 2.75. Neat. So long division allows us to actually...
Okay, now make sure you get this in your notes, please. Make sure you get this example in your notes. And what we're doing here is we're going back and we're showing you 3rd and 4th grade math in case you forgot or you never learned it the proper way.
Figure out the decimal expansion for rationals. Let's take a look at 5 over 6. Think about this together. So if I divide, I see 5 divided by 6. And again, I put a decimal point here, and then I have an army, infinite army if I need it, of zeros. I bring the decimal point straight up, like a little periscope coming up. And I say 6 goes into 5 0 times. 0 times 6 is 0. I subtract, and I see 5. I bring down one of my zeros. I see 6 goes into 50 8 times. 8 times 6 is 48. And when I subtract, I see 2. Okay, good. I bring down another 0. 6 goes into 20 3 times. 3 times 6 is 18. And when I subtract, I see a 2. Now this is very interesting, because remember, before I saw 2, I brought down the 0, made it a 20. Now I see a 2 again. I bring down a 0, and what do I see? I see a 20 again. I have a repeat. What does that mean? It means I already know the answer. The answer is going to be 3. And 3 times 6 is 18. When I subtract, what do I see? I see a 2 again. And this is going to repeat now forever. We can see that. So in fact, these 3's are going to repeat forever. I don't have to continue dividing. I can see that it has to repeat because I constantly am going to get a remainder of 2 here. And so I see this equals 0.83333 repeating forever. There's a way of actually expressing this. I want to show it to you. We could write this as 0.83, and to indicate that there's an infinite long tail of just 3's, we put a little bar on top of the 3. That means that this doesn't end here, but in fact this continues repeating 3 forever. So you can see that for some rational numbers, when you convert it to a decimal, we might actually have an infinitely long decimal expansion that actually repeats, or we say is periodic. Or alternatively, some decimal expansions for rationals will terminate after some point, like in the previous example where it ended in 0.75. So either is possible, and you have to be ready for both. I'll see you soon. All right, now we're going to have some real fun, because in this last example, I want us to take a look at a decimal that's repeating. So it goes on forever, and in fact, the 2 digits in this example actually repeat. Check it out. It's 0.63. Now, that over bar there indicates that it doesn't end at that 3, but in fact, that entire number under the over bar repeats. So this number is actually, in actuality, this is the number 0.636363 forever. And that keeps repeating, the 6 and the 3s. So very, very cool. And I want us to express this as a rational number, because we know that any decimal that ends eventually with a periodic tail like this, a repeating piece, will always be able to be expressed as a rational number. Now here's the trick. The trick is to multiply by a power of 10, so slide the decimal over, and to make the repeating thing line up. Let me show you what I mean in this case. Since I see that I have 2 digits repeating, that means that I'm going to multiply by 100, because this is tenths and this is the 100ths. So I multiply by the number 100. So I'm going to call this number x. That's the original number, and I want us to figure out how to express x as a rational. So since I see that there's 2 digits, that's in the 100th spot, I'm going to multiply by 100. Because the effect of multiplying x by 100 is the same thing as multiplying this by 100, which means this decimal point slides over 2 spots over. And so I get 63 point, and then I get 63, 63, 63. And since this was an endless list of 6 3s, this will also be an endless list of 6 3s. Namely, all the 6 3s line up forever. Well, this is awesome, because now what I can do is actually subtract. I'm going to subtract this side and, of course, this side. So if I have 100 x's and I take away 1 x, how many x's do I have? That's right, I have 99 x's. And here, if I take 63.6360 forever and subtract off 0.6360 forever, what you'll notice is all the 6 3s to the right of the decimal point all cancel. They all subtract. All I'm left with is 63 minus 0, which is 63. Well, now I can actually solve this for x. I see the 99 is multiplying the x, so to undo the multiplication, what I do is I divide. So I'll divide this side by 99. And therefore this side by 99 to keep everything balanced. And I see that x equals 63 over 99. Now, if I want to simplify that a little bit, what I could do is try to find the GCD of the numerator and the denominator. And if we try to find the GCD of the numerator and the denominator, we see it's actually going to be 9. So if I divide the numerator by 9, but also the denominator by 9, I in fact produce an equivalent fraction. And if I take the numerator and divide it by 9, I'm left with just 7. If I take the denominator and divide it by 9, I'm left with 11. So 7/11ths turns out to be the rational number that equals 0.63636363 forever without stopping. It's really cool that you can actually see for yourself the rational number that is equivalent to a repeating decimal. The secret is to multiply by a suitable power of 10 to slide that decimal point over so everything, all the repeating parts align, and when we subtract, they all subtract to 0. All you're left with is the stuff in front of the decimal point, which is some kind of whole number, in this case, since everything is positive, and we can divide and actually find that ratio. Absolutely amazing. We can produce the rational numbers that are equivalent to repeated decimals. Congratulations. I'll see you soon.